So, the last problem on external convection before we switch to internal convection. The last problem of external convection is somewhat conceptual. It assumes that we have a plate whose size is L on one side and twice L on the other side. So, you can imagine that this is the plate, this is L and this is 2 L. So, and there is a flow which is coming from this side and which flows over the plate of size L and 2 L. Now, of course, the amount of heat transfer, the question is whether the amount of heat transfer would remain independent whether I have the L face facing the wind or the twice L face, that means this facing the wind. So, if I orient my plate in this way such that the L face faces the flow or the twice L face faces the flow, would the heat transfer be different? And is there a way by which you can calculate that for what value of Reynolds number it is really not going to matter. That means, whether the flow is along L or it is along 2 L. So, we all understand that the heat transfer coefficient is a strong function of the length of the plate. In one case it sees L as the length of the plate, and in another case it sees twice L as the characteristic length of the plate. So, the question once again is, what are the conditions that are to be met such that the total amount of heat transfer from the plate is independent of whether it flow is over L or 2 L. So, it boils down to what is the condition at which the overall heat transfer coefficient, since the area remains the constant, area is always L times twice L. So, the temperature T infinity is also a constant, temperature of the plate is also a constant. So, it is the value of H which would dictate what is going to be the total amount of heat loss from the surface. So, HL and H2L, the heat transfer coefficient for the length, effective length to be L, and the heat transfer coefficient with the effective length to be twice L, are they equal? If they are equal, you would see that they are going to be equal only for a very restrictive special condition. So, what is the value of Reynolds number? What is the condition that you have to evaluate? So, that is the last problem that we are going to analyze before we move to the next subsection. So, think about this is the problem statement which I have written for you over here, that explain under what conditions the total rate of heat transfer from an isothermal flat plate whose size is L times twice L be independent of whether parallel flow over the plate is directed along the length L or it is going to be along twice L. So, this is something which we have to evaluate, but in order to evaluate that, the first part of this evaluation would necessitate that we again recall how the heat transfer coefficient varies with length, and then try to see, looking at the graph of the heat transfer coefficient, is it possible to express, is it possible to identify the special condition under which this is going to be possible, that is heat transfer from when the side L faces the flow, or heat transfer coefficient when side twice L faces the flow. In both cases, the average value of heat transfer coefficient or the value of heat transfer coefficient is identical. So, I am going to draw this graph once again of the variation of heat transfer coefficient with distance, and then we will discuss with you in order to see, in order to identify the special case when this is possible. So, let us look at how the heat transfer coefficient varies with location. So, this is my average value, since I am talking about total amount of heat transfer So, since I am talking about the total rate of heat transfer, so I must deal with the average value of heat transfer coefficient, and this is, let us say, I can plot it with x, but let us say I am plotting it with Reynolds number in this case. So, Reynolds number which is a function of x. Since HL is a function of Reynolds number x, therefore, Reynolds number. So, I can express it in this form as well, and this is how it would behave. Okay. And the transition is somewhere over here, as we all understand that this is R E X C, the transition, and for all practical purposes we take this value to be 5 into 10 to the power 5. So, this is the value of Reynolds number over which this transition takes place. So, the value of H, the heat transfer coefficient, average heat transfer coefficient based on length, and I have a Reynolds number. Let us say the faces are A and B, L and twice L. So, I have the Reynolds number which is L, and the Reynolds number which is twice L. So, when this faces the flow and when this faces the flow, I would like to see, according to this curve, when it is possible that R E L is equal to R E twice L. Since my heat transfer coefficient is a function of Reynolds number, so this, so it's I'm sorry. So, since heat transfer coefficient is a function of Reynolds number, I just have to find out some value of this where heat transfer coefficient is going to be the same. Now, let us see, is it possible, there are cases that the flow is laminar on both. So, whether you have flow along this or flow along this, in both cases they are going to be laminar. So, the Reynolds number L would simply be half of Reynolds number twice L, which is universally true since I have L on one side and the size is L and 2L. So, the Reynolds number based on 2L would simply be twice that of the Reynolds number based on L, everything else remaining same. So, let us concentrate on this part of the curve. Is it ever possible that, let us say, if this is R E L, so of course, here would be some point which is going to be R E twice L, which would simply be twice of this, and you get a value of H bar L in this is going to be your H bar L. Whereas, for the case of Reynolds number L, this is going to be your heat transfer coefficient. Since heat transfer coefficient is a monotonically decreasing function of Reynolds number in the laminar zone, you will never get the relation that for two values of Reynolds number where one is the double of the other, the value of the heat transfer coefficient, average value of the heat transfer coefficient in both cases would turn out to be the same. This is very important. I will explain it one more time. The heat transfer coefficient decreases as Reynolds number increases. So, if I fix my Reynolds number at some point, my Reynolds number based, this is Reynolds number based on L. So, Reynolds number based on twice L would be some point after that, and because of the dimensions involved in this case, R E L is simply going to be half of R E L. The heat transfer coefficient keeps on decreasing. So, it is never possible to have the same heat transfer coefficient when the curve is monotonically decreasing. So, we will never have a situation in which the flow is laminar on both the plates in both the orientations, still it is going to give you a value of equal value of h bar L or h bar 2L. So, coming back to this figure, you do not get, it is not possible to satisfy the equality of h bar L when when flows are laminar. So, this is my case 1, I will call it as case 1. Now, case 2 is something which I call it as, this is my case 2, where the flow is laminar on one side and it is turbulent on the other side or mixed on the other side. Okay. So, this is, if this is my R E L and if this is my R E twice L, there may be a possibility that both of them would give rise to the same value of h bar L. So, if the flow is laminar on one side, as is shown by R E L, and when it is oriented in the reverse way, when it is oriented in this way, this is your Reynolds number. When it is oriented in this way, this is your Reynolds number. In this case, the flow is laminar. In this case, the flow remains laminar up to certain point and then changes to turbulent. So, pictorially, the situation may look something like this, which would probably, as the figure suggests, give us the same value of h bar L. So, my case 2 in this case is laminar on shorter plate, turbulent or mixed flow on longer. So, as the figure suggests, it is possible, probably I am going to get a situation in which this is half of this, but they are going to, the nature of the curve would dictate that the value of h bar L in both cases were same, which was not possible when both were laminar. You are never going to get the value of h bar L in this case to be equal to h bar L, but the nature of graph dictates or suggests that this is possible. So, case 3 then remains mixed on both, mixed flow. So, this is something which is possible, mixed flow on both. Now, if it is mixed flow on both, then what if it is like this? This is one, this is the other. So, if this is my R E L and if this is my R E 2L, then both of them would give rise to the same value, may give rise to the same value of h bar L. So, if both are mixed for R E L as well as of course, at R E 2L, the nature of the graph, nature of the H L variation with Reynolds number would allow the possibility that the value of H would be the same in both cases. So, I think I have considered all possibilities. The first possibility being the flow being laminar on both, which would not allow the equality of H bar L. The second is laminar on one, mixed on the other. the shape of the curve, shape of the H versus Reynolds number curve, average H versus Reynolds number curve would allow that. The third is when both are in the mixed flow range. There also the sudden increase and the gradual decrease of the convective heat transfer coefficient in the turbulent region will allow the will allow the possibility of equality of the value of heat transfer coefficient. So, laminar region it is monotonically decreasing. So, it is never going to be possible. When it hits turbulence, it shoots up, the value of H shoots up, and then with increase in the value of Reynolds number, with increase in the value of the axial position, increase in thereby the increasing the value of the boundary layer thickness, the resistance keeps on increasing, and slowly the value of heat transfer coefficient in turbulent flow will start to decrease with increase in the axial distance, that means with increase in Reynolds number. So, the fall of H in the laminar zone is sharp, the sudden rise of H because of the onset of turbulence is also sharp, and therefore, thereafter the fall of the H with Reynolds number or with X is gradual. That is in essence the nature of the H versus X or H versus Reynolds number, average H, H bar. So, this specific nature of Reynolds number curve would allow the equality between this L and 2L or 2L and L for the case of laminar on one, mixed on the other, and mixed on both. These are the only two valid viable possibilities at which the value of the average heat transfer coefficient will be identical, and therefore, the total amount of heat loss will be the same. So, now we have to physically do the problem and find out what is the value of the Reynolds number for which this is possible. So, I will take case 2 and case 3, I do not need to consider case 1, case 2 and case 3 and find out the value of the Reynolds number and the value of the size for which this is possible. So, let us start with the first case, the case 2 first. The case 2 simply tells us that it is going to be laminar and on one and mixed on the other. And if this in what we are looking for is H bar L is equals H bar 2L, and we also understand that R E twice L would obviously be R E L. So, these are our this will always be valid, and we are looking for these two. Now, since this is in laminar flow, I am simply going to use the Sherwood number relation for laminar flow. So, this H L would be 0.664 and K by L, Reynolds to the power half, Prandtl to the power 1/3, and for 2L it is going to be K by 2L. This is in mixed flow. So, the corresponding mixed flow equation is 0.037 Reynolds based on twice L to the power 4 by 5 minus 871 Prandtl to the power 1/3. I am sure you recognize these two. This is for the laminar and this is for the mixed, and simply I multiplied K by L in one case, and so this is laminar Nusselt number relation, average Nusselt number, this is mixed Nusselt number, and I simply put K by 2L in here. Once you put this RE2L to be equal to twice of REL and simplify, the result comes to be 664 Okay. So, this is the relation which you obtain from there. Now, we identify that REL has to be less than 5 into 10 to the power 5 and R, because since it is in the laminar zone, it has to be in the laminar zone. So, REL must be less than this, and RE2L, which is twice REL, must be greater than 5 into 10 to the power 5. So, Reynolds number considering the laminar in this case has to be less, and for the mixed flow my Reynolds number must be greater than 5 into 10 to the power 5. So, RE2L, which is the Reynolds number in this case, which is equal to twice REL, must be greater than 5 into 10 to the power 5. So, this narrows down the value of the Reynolds number between this range. So, this is the range in which my Reynolds number should reside, and from a trial and error solution, this equation cannot be solved directly. From trial and error, with by assuming a Reynolds number in this range, you would be able to see that Reynolds number is to be equal to 3.2 into 10 to the power 5. So, the steps are simple. Laminar, when you have this case, L is facing the flow. So, this is L, this is 2L, and mixed when you have this facing the flow. So, that we have identified previously. So, this, since it is laminar, I use the laminar Nusselt number relation, multiply it with K by L. This side I use the mixed Nusselt number relation, multiply it with K by twice L. Just remember why we are using twice L, because the length involved in this is twice L, whereas the length over which the flow takes place involves L. Do this, identify the range in which your Reynolds number must lie. From a trial and error, find out what is the value of what is the Reynolds number value for this specific case. Now, we come to case 3. Case 3, where you have this in one case and this in the other case, but in both cases they are mixed flow on both. This is my case 3, mixed flow on both of them. So, if it is mixed flow on both, then K by L 0.037, Reynolds number based on length in this case to the power 4 by 5, Reynolds number based on L only, PR to the power 1 by 3. Now, this becomes K by twice L, since this is the length here, 0.037, Reynolds number based on twice L to the power 4 by 5 minus 8071 times Prandtl to the power 1 by 3, and we understand that R E twice L would simply be twice R E L. So, when you put that in here and simplify, what you are going to get is this would give you a Reynolds number to be equal to 1.5 into 10 to the power 6. So, if your value is Reynolds, if the value of the Reynolds number is 1.5 into 10 to the power 6, when both are in the mixed flow range, then it becomes immaterial whether L faces the flow or twice L faces the flow. So, for a value of Reynolds number, when you have laminar on one side and mixed on the other side, the value of that Reynolds number turned out to be 3.2 into 10 to the power 5. You would get equality of heat transfer irrespective of which side faces the flow. Secondly, for the case 3, for a Reynolds number of 1.5 into 10 to the power 6, you get the same thing. That means, whether it faces L faces the flow or twice L faces the flow, the average heat transfer coefficient in that for those two configurations will be identical, and therefore, the total rate of heat transfer from the object would be identical as well. So, the beauty of this specific problem is it tests your concepts of the variation of heat transfer coefficient with Reynolds number. How would the heat transfer coefficient change with Reynolds number in laminar flow, how it increases sharply in turbulent flow, and how it gradually decreases thereafter. So, from a sharp decrease in Reynolds number for the case of laminar, sudden increase and then gradual decrease. These characterize the behavior of heat transfer coefficient in laminar and in mixed flow. So, once you have this picture of heat transfer coefficient in mind, you will never do any mistake in selecting the ideal relation for calculating the heat transfer coefficient. And you would also be able to think, looking at the shape, of more advanced problems which would test your knowledge about your understanding of the variational behavior of heat transfer coefficient with the length. And finally, the last part of the question was, is this valid for any type of fluid? That means, the value of Reynolds number, for some value of Reynolds number, you are going to get this directional independence. Is your result, does your results depend on the type of fluid that you have? If you consider the development of the problem, nowhere we have assumed what kind of liquid is this. Okay, whether it is air, whether it is water flowing over the plate, glycerol flowing over the plate, the fundamental result in terms of Reynolds number will be the same. So, this underscores the importance of Reynolds number as a similarity parameter. A similarity parameter is such that it allows you to compare results using different fluids, and it would tell you that if you keep the Reynolds number the same, the value of everything else, the nature of everything else, including flow pattern and in this case heat transfer, everything will fall in line. So, this result that we have obtained is independent of the physical properties of the fluid. Any fluid that has a Reynolds number of 3.2 into 10 to the power 5 would give you the same result, directional independence of whether L faces the flow or whether twice L faces the flow. Or in the case of mixed flow, if it is Reynolds number is 1.5 into 10 to the power 6, you will get the same result irrespective of the flow of the fluid. So, this more or less concludes our discussion on convection in an external flow. So, if it's we have mostly concentrated on flow over a flat plate, and while designing heat exchange equipments, we have to see what kind of additional constraints, mostly empirical, that we need to add when the flow is over a curved surface. For example, if you have a number of tubes, so called banks of tubes together, and if you have cross flow or parallel flow, what would be the relation for such cases? But those are informations which are available in the text. Whatever we have concentrated so far are on the understanding that you always start with laminar flow, and then at some point you change over to turbulent flow, and therefore, how to calculate the heat transfer coefficient in laminar flow? The approach that we have used is semi-analytical, only towards the end we have used some sort of a correlation for the Prandtl number dependence of the temperature gradient. If you look back at your class notes, you would see that what we have done, that dt d eta was expressed as a function of Prandtl number to the power 1/3, if I remember correctly. So, that is one thing, and when we changed over to turbulent flow, we used the Reynolds analogy and the modified Reynolds or Chiltern-Colburn analogy, which are extremely important because they allowed us to use relations obtained for momentum transfer from fluid mechanics to be used for the case of heat transfer. So, you need not solve for the complicated coupled heat transfer equations and the momentum transfer equations together. Based on your knowledge of turbulent flow momentum transfer, you can obtain the relation for turbulent flow heat transfer. That was the beauty of the analogy between heat transfer and momentum transfer. And later on, when you study mass transfer, you would see that the same analogy is applicable to mass transfer processes as well, but we are not considering that at this moment. But the same Reynolds or modified Reynolds analogy is equally applicable for mass transfer. So, from the analogy we obtained the relations for turbulent flow Nusselt number relations and mixed flow Nusselt number relations. So, from next class we will start our discussion on internal flows, flow that are taking place inside a tube, how to handle them.